Yeah, there's a question about how deep we should go because we could obviously spend hours fully exploring the topic, but I'll give you the view from 30,000 feet. So I wasn't really looking to find anything about drug safety testing. In fact, when I started the project, I didn't have any intent to go anywhere medical at all. I was really just trying to answer an evolutionary question that I found interesting and about which I had a sudden flash of insight. The question was, why do creatures like us grow feeble and inefficient with age? The technical term for it is senescence. The common parlance term would be aging. But I was interested in why we senesce. And that is a question that has had a proper theoretical answer since 1947, when George Williams wrote a paper explaining the basic underlying trade-off, but had never had a practical example found. And one day I was sitting in a seminar, and a student who didn't really know anything about evolution, a guy who decided to try out the seminar in some spare time he had from the cancer lab he was working in, gave a talk about cancer. And I realized that there were two different groups of people, one studying aging or senescence, the other studying cancer, who had become focused on the exact same mechanism, but they saw it in exactly inverse terms. So the people who were studying aging looked at something called telomeres, and they thought that the fact that telomeres, which are repetitive gene sequences at the ends of chromosomes, the fact that those sequences were limited and therefore limited the number of times cells could reproduce, that was probably a curable cause for senescence. In other words, they wanted to remove the limits on the telomeres. And the other group was studying cancer, and they had discovered that those limits had been lost every time they looked into a cancer. And so they wanted to institute better limits. And each group thought that they were about to extend human longevity by messing with telomeres, but they clearly weren't spotting the other half of the puzzle, which suggested that actually the answer I mentioned from 1947, George Williams, was correct, that there was a trade-off, and that in fact, the reason that we don't unlimit our telomeres and have infinite cellular replacement is that we would be almost immediately overrun by tumors, right? So we have an elegant system that causes almost all of the tumors that we would otherwise get to arrest themselves, and you're never aware of them. But the cost is you can't repair your tissues indefinitely throughout life. So that's the question I was studying. But as clean a story as that is, there was one huge obstacle, which was that mice were understood to have extremely long telomeres, much longer than human telomeres, and yet they had very short lives, which was presumed to falsify any such model. And I looked at this and I thought, there are too many places where this model that places tissue repair and tumor suppression as opposing forces in a trade-off, there are too many questions that would be solved if it were true. And there was only one piece of evidence that suggested it was false. Maybe there's something wrong with that piece of evidence. And it's when I went looking for what might be wrong with the idea that mice have very long telomeres and short lives, that's where I tripped over it. And by it, I mean, I went from an area that was more or less just of academic interest or scientific interest, and I moved accidentally into an area where there was a huge amount of money at stake. That's the point at which science went insane around me, and I grew up. I learned the lesson about what happens to science in the context of money, and it ain't pretty. So, to your question, Robert, it turned out that the problem that I had identified was solved if you hypothesized that mice do not, in fact, have long telomeres, that wild mice have short telomeres, and that it is laboratory mice that have long telomeres, telomeres that have been elongated as a result of the breeding protocols that we use to produce laboratory mice. Now, the reason that the literature concluded that mice have long telomeres is that there were many tests that showed that, in fact, the telomeres were always long. But what was unclear was that they had all gotten their mice from the same place. And so the protocol that had changed, that had caused the evolution of long telomeres in mice, then became a pseudo replication, meaning that many laboratories were sourcing their mice and coming up with the same answer, but not because it was representative of nature. Instead, it was representative of this particular source of mice. So, to make a long story short, um, I put that hypothesis on the table. I shared it with somebody who had been studying telomeres, and she tested the hypothesis. She put a graduate student on the work. That graduate student tested the hypothesis that wild mice had short telomeres. And I got a very excited email reporting that, in fact, the hypothesis was true. Mice actually have short telomeres. So that's the good news. That meant, oh, my hypothesis about telomeres, senescence, and cancer is likely right because the one obstacle was now gone. But the problem is that had dire implications for medicine and, in particular, pharmacology, because when an animal, like a mouse, has very long telomeres, what that means is that it is extremely prone to cancer, which is true. Laboratory mice all die of cancer if you give them time. But they are also extremely resistant to tissue damage in a way that humans aren't, because they effectively have an infinite capacity to replace cells. So if a poison doesn't outright kill a mouse, the mouse will show far fewer pathologies than a human because it can replace its tissues in a way that a human cannot. Now, that piece of news should have caused a change in the way we studied drug safety. It should have caused us to reinvestigate every drug that had been tested on these broken mice, again, using mice that were not broken, to see if the drugs that we had released were in fact safe for humans in the way that we thought they were. Instead, this caused what appears to me as an outsider to be a massive cover up in which we pretended that the mouse telomere issue was not a problem. We didn't go back and recheck any drugs. We never connected the dots with respect to Vioxx, Fen-Phen, Seldane, erythromycin, all of the drugs that had done heart damage when they were released into people, which we did not expect based on animal testing. So what I saw was a scientific system that stared down a major error that it had produced. Initially, I assumed that error was accidental, but instead of curing it, I believe what happened is the pharmaceutical industry realized that they had a mechanism for getting through safety testing with drugs that were poisonous, and that was good for business. And so they preserved it. And as far as I know, this problem persists to this day.